Okay, so today we will start with the third unit, that is image enhancement in filtering, filtering in the frequency domain. In earlier section, in earlier unit 2, we have seen image enhancement in spatial domain. Okay, so here we will deal with the frequency domain image enhancement. These are the contents for your third unit. So you will see what is image enhancement in frequency domain, the basics of filtering in frequency domain, the filters, smoothing frequency, types of filters, and so on. What is the benefit of applying each category of filter, that we will see in the first part of the unit. Then we will see what are the various domain filters. Uh, We'll study about ideal low pass filter, Gaussian low pass filter, Butterworth low pass filter. Then we will see about sharpening frequency domain filters. Here we will study about the high pass filters. So ideal high pass filter, Gaussian high pass filter, Butterworth high pass filter, and homographic filtering we will see. I have given one link also. It consists of the NPTEL video. So here it is the main lecture that you can see where the overall image enhancement in a frequency domain is handled. So if anybody is interested, you can go through this link as well. Let us just recap what we have studied in earlier unit under image enhancement under the spatial domain. So as you know that image can be represented in the form of a 2D matrix, where each element of the matrix, it represents a particular intensity of a particular pixel. So this state of 2D matrices, it shows you the intensity distribution of the complete image, which is called as the spatial domain. Okay, so whenever you know the intensity distribution of the image, it always falls under the spatial domain. So for example, the grayscale image, if you represent a 2D matrix for this image, so here it can be like the this pixel is having this intensity, this pixel is having this intensity. Okay, so it is nothing but just a 2D matrix representation of the pixel intensity values of the entire image. So this is the spatial domain for grayscale image. If you consider the RGB image, then the spatial domain of RGB image is represented as a form of a 3D vector of 2D matrices. So there are multiple vectors, you can say, for RGB image. So each 2D matrix, it contains of intensities of various single color. So for red, for green, and for blue, you will be having a individual 2D matrices. So this is your spatial domain for RGB image. Here the each pixel intensity is represented as I of x comma y, where xy is the coordinate of the pixel in that 2D matrix. The different operations that are carried out in image processing on spatial domain are based on the pixel. Okay, so you do pixel wise operations. For example, if suppose I am having a transformation function of adding 5 to all pixels, so the 5 is added to each and every I of xy, so that I dash of xy is equals to I of xy plus 5. So I can say that I dash of xy is the new intensity after we add 5 to each and every pixel of the input image I of xy. So here all operation is carried out at on pixel level. So that's why it is called as a spatial domain image enhancement. Let us see about what is the frequency domain image enhancement. Frequency domain is nothing but these are the methods which are based on the Fourier transform of the image. So roughly the term frequency in the image, it tells about the rate at which the pixel values are changing. Okay, so let us consider if this is the input image, the first row where the cartoon picture is there. So this picture is and the another picture below it. So this picture is the conversion of the input image from a spatial domain to the frequency domain using the Fourier transform. So if you apply a Fourier transform of this image, then your resulting image will look like this, where you are not able to identify any object and all, but you can see the frequency distribution. Okay, Similarly, if there is another blurred kind of image of the same cartoon, so its Fourier transform will give you something different image. So here in this image, the bright spots near the center, this corresponds to the low frequencies. Low frequencies, like you can say that the smooth areas of the image. Okay. Then the dots that are quite away at larger distance from the center point. So this will represent the high frequencies. So you can consider these as the edges and the fine lines. Okay, fine. So brighter points in the frequency domain, these are that means the strong it shows the stronger presence of those frequencies, I can consider like this. So this is the frequency domain. Let us see something more about the frequency domain in image processing. So, if I compare the spatial domain versus frequency domain, so spatial domain, this is like the original image itself, okay, where the pixels are directly represented with the pixel values or the brightness levels, I can say. But in frequency domain, instead of looking at the pixel values directly, we represent an image in terms of how quickly the pixel intensities they do change, or we can observe what are the variations at different locations, what are the edges, what are the patterns of the image that we can quickly identify, right. Here in frequency domain, there are two terms, low frequency and high frequency. Low frequency is nothing but it is like the slower changes or low intensity changes from smooth areas like you have sky, skin. Okay, so there is, I can say that intensity changes are very slow. You can't find out there is a drastic change, right. So that is the low frequency. So it is like a similar texture is present throughout the image. Okay, so most of the times the background is having a low frequency. Okay, because it is having the almost all the pixels are looking as if the similar, so there is no much intensity change between the two pixels, I can consider like this. For then high frequency, this shows the rapid changes in the image. For example, edges are there, fine lines are there, noise is there, sharp transitions are there, right. For example, if I consider an image of a sky in which there is a bird, so if you can identify wings of a bird, so you are able to find out the wings of a bird, right. So there is a high transition, right. So there are sharp edges present, so this is the high frequency image. I hope you are getting it. If whenever we are dealing with the frequency domain image processing, there is always a concept of Fourier transform into picture. So Fourier transform, it converts the image from the spatial domain, that is pixel values, into the frequency domain. So for example, the sinusoidal waves. Okay, so sinusoids of the different frequencies, this is nothing but my frequency domain. So you can just think of an example of Fourier transform. Like let's say you are listening a song. So instead of looking at the sound wave directly, you can break it into the bass value, the mid, the treble, likewise, right? So the here you are dealing with the uh, what you can say like a Fourier transform of that song. Fine. So similarly, as you can process on sound waves, so similarly you can process on images as well, where the image can be broken into the low frequency and high frequencies. Why this is so important to study this frequency domain? Uh, Working on the frequency domain, it makes easier to remove the noise that is present. For example, very high frequency components that can be considered as a noise. Then to enhance the edges. Here also high frequency emphasis is given. Then I want to if the compress image, so here I'm dealing with only keeping the important frequencies into the storage, and rest of the things I'm going to omit. So that's why the frequency domain analysis is important. Then I want to filter the images using the frequency based filters depending on low pass, high pass and band pass. These are the categories of filters we will see in upcoming sessions. So in short, spatial domain deals with the actual pixel values, that is what we are able to see, it deals with that. In frequency domain, how quickly the intensity changes are happening, what details are present right now, so that is dealt. Fourier transform, it helps the switch between these two. And here is I'm having, okay, this diagram. This diagram is the conversion of a spatial domain to frequency domain conversion. Okay. Okay. While working with the images, if we compare spatial versus frequency domain, so spatial domain is most common, we can say. Frequency domain is sometimes used, and but it is more effective. In terms of spatial domain, processing is done directly on pixel, as I already told. Here, the operations that are performed on spatial domain are very simple. So, for example, adjusting brightness, adjusting contrast, or performing filtering operation. Right, we have seen in second unit what are the various filtering operations we can perform. Then it is easier to visualize. This is because the changes happen directly on the pixel intensity value. For example, histogram equalization, gray level transformations, spatial filtering, where smoothing can be done, sharpening using various masks can be done. We have seen this, right? In terms of frequency domain, the processing is done on the frequency representation of the image. This requires certain transformation function to convert and given image into the frequency domain. So most of the so always we use the Fourier transform for representation of the frequency domain of the image. This is again useful for the task where the frequency separation is very important. For example, low frequency to high frequency. Examples include of this are noise removal in the image, which requires a low pass filtering. Then if I want to do edge enhancement, whenever my application deals with extraction of edges or extraction of the meaningful objects, so there also I need to work on the edges. So here I will use the high pass filtering. Another application in which the image compression is my requirement. So here I want to remove less important components from the image. So that's why I need to deal with the frequency domain. If there are so many, if there are these domains are existing, then how to decide which one to use? So spatial domain, it will always give you the quick results, and whenever the simple adjustments are there, so that time you can consider the spatial domain. So simple adjustments that are on the pixel level, the pixel intensity values. So that time you can choose for the spatial domain. For frequency domain, you can decide when it is as the more effective for global operations like noise removal, noise reduction, sharpening of the image, analyzing the textures, analyzing the patterns that are present, or object extraction. So that time the frequency domain you will be working with. Is it clear, everybody? Someone please acknowledge. I just told you the basic behind the spatial domain, the frequency domain, the revision of the spatial domain, and something about the frequency domain, when to use, what is the comparison, likewise. Someone please acknowledge me. Is it fine? Apurva, you there?
Yes, ma'am, understood.
Okay. This is the same thing. Okay, let us see about the image enhancement in spatial domain. We are starting with the actual contents of the third unit now. So here there are certain steps involved whenever we are considering the image enhancement in spatial domain. So first step is the transformation step. Here we convert the given input image, which is in a spatial domain representation, to the frequency domain using the Fourier transform. This is always there. Okay, you always use the Fourier transform whenever you want to convert the image into the frequency domain. So this represents an image in terms of the its frequency components. For example, in terms of the low and high frequencies of the image. Next step is the filtering step. We apply the filters to selectively modify the frequency components. We use the low pass filters, which allows the low frequencies, then it blocks the high frequencies, which will result in the blurring of the image, or reducing the noise from the image. Okay, then we can use the high pass filters, which allows the high frequencies and it blocks the low frequencies, and it results the sharpening of the image. It will result in edge enhancement of the image. Okay, so depending on your need, you can process. You can select the filters and you can modify the frequency components of the given image. Next step you will perform is the inverse transformation. So use the inverse Fourier transform to convert the processed frequency domain back to the spatial domain, which will result in the enhanced image. The key advantage over here is it allows the targeted manipulation of the image details by controlling different frequency ranges. It provides more flexibility as compared to directly modifying on the pixel values. Okay, unlike the spatial domain techniques, the frequency domain techniques, they use the Fourier transformation. At low frequencies, they represent low frequencies like to represent the smooth areas that are present, the background, and the slow intensity variations. For high frequency, it represents edges, sharp transitions, and fine lines, as I already told you. So by manipulating on these low frequency and high frequency components, we can enhance the overall details of the input image, where we work on the edges and noise. So to enhance details, that means we are working on edges, and removing noise, that means we are performing the smoothing operation. So why frequency domain is very important? This is because the image can be represented as a combination of various frequency components, low frequency and high frequency, where I have a background, I have the smooth regions, I have the edges present, I have the noise present, I have the objects, I have different objects, like different objects of different intensities. So that's why frequency domain study is very important. If I consider, okay, as I told you, suppose I'm having a photograph of a sky in which the bird is there. So the sky is like my background, and the bird is, which is my object, where the edges of the birds are very sharp. So that picture, the edges of the bird, that is called as the high frequency, and the background, which is let's say of a light blue color, so which is called as a smooth appearance, overall smooth appearance. So this will represent the low frequency. So this is the example you can give whenever you are asked, just explain what is the frequency domain given a picture, and if you want to figure out what is the high frequency and low frequency, accordingly you can just explain. Okay, so if you want to smooth the image, we should reduce the high frequencies. If we want to sharpen the image, then we should increase the high frequencies. Okay, so that's all. This is the main thing in these two operations. Fine. You can just note down this somewhere. In smoothing, we focus on high frequencies reduction, and in sharpenings, we focus on increasing the high frequencies, or the whatever frequencies are there. So, how to work in the frequency domain? So, this process has three basic steps. The first, transform the image to frequency domain using Fourier transform, which will give you the spectrum where each point will represent a frequency that is present in that image. Then in second step, you multiply the spectrum by the filter function h of uv. Just ignore this 3 times h of uv. Yeah? It's simple h of uv. So here this filter function, it decides which frequencies we want to keep and which frequencies we want to discard. So that is decided by the filter that you are choosing. Then apply the inverse transform, apply the inverse Fourier transform, so that you transform you transform back to the spatial domain. So this will give you the processed image. The formula to perform these operations is g of xy, like the processing in the frequency domain for the input image. Okay, so g of xy is equals to f inverse of f of uv comma h of uv. Here here f of xy is my input image. I know that input image, so I'm just taking it. Then I will apply the Fourier transform of the image with f of uv. Then I will apply the the product of the filter operation and the Fourier transform, and result of this is given to the inverse Fourier transform. Okay. So g of xy is my final enhanced image, I can say. You have a concept of a separate concept of smoothing in a frequency domain under this chapter. So here the meaning of smoothing, as I told you, smoothing deals with blurring of the image, or where I deal with reducing the noise in the given image or removing the noise. So this deals with the smoothing operation. So here I am basically focusing on removing the small details or the less important details, or I want to remove the sharp transitions, or I want to reduce the effect of sharp transitions rather. If there are certain fine variations, like similar, lesser kind of variations are, then how can I discard it so that the overall image appearance will look more uniform. Okay, so here the goal of the smoothing is to reduce the high frequency noise that is present while preserving the general structure of the image. Okay, so if I'm performing smoothing operation, let's say on a room, I'm having a picture of a room. So if I want to perform the smoothing operation, what I will focus on? Yes, can anyone tell me? So here I would like to preserve a background, and I will just lesser what I will do is I'm going to manage with the overall appearance of whatever objects are present. Those are having the high frequency, right? So if I can suppress the effect of overall appearance of various objects into each other, so that means I'm performing a kind of smoothing over there. Fine. This thing I already told you, the high frequency, low frequency, and so on. Just go ahead. So let us move to another point, that is low pass filter. We are using various kinds of filters. Okay, so in smoothing operation, whenever I want to perform smoothing, so in smoothing I'm always using low pass filters. So definition of low pass filter is nothing but a low pass filter, it allows the low frequency components of the image to pass through, and it blocks the high frequencies. The appearance of the high frequencies I am going to block, which will correspond to the high frequencies are nothing but your edges, objects, fine details, noise present, likewise. The purpose of using low pass filters is to reduce the noise, to smooth out the sharp intensity transitions that are present in the image, to blur the fine lines while preserving the general structure. So, this is the basic low pass filter objective. There are several categories of low pass filters. Let us see those. The first category is ideal low pass filter, which is having ILPF as a short form, and this is the standard one. So wherever in books also, if you find out this word, so just remember this is ideal low pass filter. Its working is it completely removes all the frequency components beyond a specified cutoff frequency. That cutoff frequency is denoted with D0. So you can determine what could be the cutoff frequency, and whichever components in that image those are having the frequency beyond that cutoff, you can simply skip those. Okay, so whichever number of the objects are there, whatever number of the intensity might be there, if you find such a frequency component which is beyond this D0, directly skip it. So that is how the low pass filter is working. So it will pass the frequencies inside a sharp circular boundary of the frequency spectrum. The characteristic of ideal low pass filter is they specify or they provide very sharp cutoff in the frequency domain. It has a spatial domain drawback as it causes the ringing effect. Ringing effect is nothing but like, for example, it's like ripples around the edges, right? I hope you are able to recollect the ringing effect. Like overall appearance of the pixels around the edges. That is called as the ringing effect, right? So here the use case in which the low pass filter, the ideal low pass filter is used is like whenever I want to have the strong suppression of high frequencies, but it is not suitable when the edges preservation is important, right? Okay, I want to study the edges present, but I want to at the same time I want to suppress the effect of edges also. So here it is a very tricky thing because I need to deal with the ringing effect also. Another category of low pass filter is Butterworth low pass filter, which is BLPF. Here, the working of it is it provides a gradual transition between the low and high frequencies. So, this is controlled by filter order. So, I can choose different filters with various orders. Okay, so here depending on which order I am choosing for my filter, the effects will be different. Okay, so if I use the low order filter, then I will have more smoother transitions. Okay, if I am using the high order filters, so it will give me the sharper cutoffs. So it is like the results are as good as equal to your low pass filter, ideal low pass filter. The characteristics of this Butterworth low pass filter is it is giving you the less ringing effect as compared to your ideal low pass filter, so that it balances between the sharp cutoffs and the smoothness. The image should not be too much sharp or image should not be too much smooth. That is my if my application needs this kind of thing, so in that case I can go for the Butterworth low pass filter. So it is like when I want to preserve the details of the image whenever I'm having such a scenario, so I am choosing that enhancement strategy. Okay, so I can go for the Butterworth low pass filter. I will show you various diagrams also, that if I apply different kinds of ordering of filters, how the image will look like and so on, so that you can determine how it works actually. There the idea will be more clear. Another category is its Gaussian low pass filter. So here the working of it is based on the Gaussian function you are using, that is in a frequency domain. Here what you can say, like there are no abrupt cutoffs between the image objects. So wherever such a requirement is there, even though I have the different objects in the image, but there are no abrupt cutoff, because I know if how can I identify different objects? There are the cutoffs, right? Every object has its own threshold. Right, for example, if I'm having an picture of a room, So that room has light, that room has fan. So fan and light, they have their own threshold values, right? I hope you are getting this. So it is like a cutoff of their own individual frequency values I can consider. Okay, so I am processing the image such that the overall appearance, I am not able to distinguish between the fan and tube light or fan and the chair likewise. So overall everything looks very smooth. Okay, so this kind of thing is there. So I am simply suppressing each and every object's effect. If this is the scenario, this is the Gaussian low pass filter. So this provides you the smoothest transition among all low pass filters. It won't have the ringing effect in the image. This is because we are suppressing each and every object's appearance. Okay, then it preserves more natural looking of the image. The use case is it is most used in whenever we want to do certain pre-processing, the noise reduction or the blurring before the image segmentation. So these are the use cases. The results of smoothing is your noise that is present in the image is reduced, so that image looks more cleaner. The image becomes blurred, so that is the effect of smoothing. Okay, so this is because the fine details and the sharp edges, these are lost. Fine. These are useful as a pre-processing step for image segmentation, for object recognition and for feature extraction. So this step is very important if you are having these kind of applications in your mind. So you have to always perform the smoothing whenever you are dealing with these applications of image processing. Is it fine with you? You understood what I told? Here a kind of image enhancement where I want to have a blurred image, that is the smoothing. Generally what you may think image enhancement is nothing but just always increasing some appearance and so on. But sometimes my application may demand I want a blurry version of the image. Okay, so that means I want to perform the smoothing. Any doubt in this? Okay, the same thing, the same slide is there. So noise reduction, it deals with removing the high frequency noise, for example in your scanned images or medical images. Okay, blurring, it is used before the image compression, so that to reduce the unnecessary details. Then pre-processing, it is a kind of smoothing before the edge detection or image segmentation. So here the examples wherever the frequency smoothing filters are used are like in satellite images, smoothing filters to remove the tiny speckles. These are caused by the sensor noise while keeping the main and the important features. Okay, so in short, low pass filtering, it deals with smoothing, which keeps low frequencies, it removes the noise, it removes the high frequencies, is and overall it reduces the noise but it blurs the edges. And in high pass filtering, which is called as the sharpening, it keeps the high frequencies, it removes the low frequencies and it enhances the edges, the appearance of the edges, but it can increase the noise that is present. Okay, this is because it is keeping the high frequencies into the image. Fine, that's why it may result in increase in the noise of the image. I hope this is clear with you. Is there any confusion in anybody's mind? If you have any question, you can ask it. And just take a pause if you have any questions. So smoothing deals with low pass filtering, sharpening deals with high pass filtering. Smoothing deals with reducing noise, sharpening deals with increasing the noise. Okay, smoothing deals with keeping the low frequencies, sharpening deals with keeping the high frequencies. You can remember like this. Smoothing blurs the edges or it blurs the image. Sharpening, it it won't blur. Fine. It will enhance. It will enhance the edges. I hope this is clear. So this is the diagram of how the filtering in frequency domain operation looks like. You have the input image, you do certain kind of pre-processing, then the pre-processed image is given as input to the Fourier transform. So here the Fourier transform function, the result of Fourier transform is given to the filter function denoted with h of uv. Its output is given to the inverse Fourier transform. Okay, here this operation will be nothing but the product of f of uv and h of uv. Then it is given, this output is given to the inverse Fourier transform. Then this is given to the post processing, which will be giving you the enhanced image. Okay, we will see further points. We still have time, no? Yes. Anybody is having doubt? Someone please acknowledge.